This is the final video for Chapter 12, Differentiation, and this goes with sections 12.10 and 12.11 in your workbook. The first section that we're going to look at is sketching gradient functions, and then we're going to do some work on using maximum and minimum for optimization. So this first little bit is about sketching gradient functions. When you're sketching a gradient function, what you need to do is consider what the gradient is doing. So the first thing we're going to do is going to look at this first curve, and you can see looks very much like y equals x cubed to me. So the first thing you notice, and I'll do it in colour, that this point, this is a point of inflection, that's where the gradient is 0. So if I'm transfer that over, that's when the gradient is 0. Okay, now the next thing we need to do is consider what's happening. Now notice here, the gradient of this graph is always positive, and same here, always positive. But as I go down the graph, it's getting more and more positive. So when I draw this, I want a graph that is more and more positive. So in other words, I'm going to get something that looks a bit like this. It gets more and more and more positive, and same here, more and more and more positive. Oops, not very good graph that. In fact, I'm going to rub that side out and do that one again. So that gets more and more positive as we go along. Okay, now what you can see, if this graph on this side is cubic, this graph is quadratic, and that is because that ties in, because remember, when you differentiate to cubic, you get a quadratic. Let's look at the next one. This one, you can see that this point here, the gradient is 0, so I'll mark that. So when x is 0, x on this side is 0. And here, this is positive, 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 but it's getting more and more positive. And this, of course, is negative, negative, negative. So the positive side is going to look like this, and the negative side will look like this. Okay, so you can see it matches up. Okay, and again, this is a quadratic, and this is linear, and that goes when you differentiate. This one, you can see first of all that you have an asymptote at the y-axis, and if you have an asymptote at the y-axis, you're still going to have an asymptote on your gradient function. Same asymptote, vertical asymptote. You can see here that this is negative, 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 and negative, negative. The gradient all the way along this graph is negative. So in other words, it's going to be underneath, but it's getting more and more negative. So we're going to get something that looks like this. Right. Okay, because it's all negative underneath. This one, again, let's look at the next one. So this point here, that's when x is just less than -1. That gradient is 0, so I'll put that there. This point here, when x is just greater than 1, that's also 0, so I'll put that there. When we're here at the origin, we've reached our maximum negativity. It's actually another point of inflection, but not a stationary one. When you've reached your maximum negativity, that's another point of inflection. So that could come down, say, to about here. And then, of course, this side, positive, positive gradient, lots of positives, and it's getting more and more positive. And this one, it's getting positive, and again, as x tends to negative infinity, it's getting more and more positive, 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 positive. So in other words, and this side is going to be positive. So it'll look something like this. Now I apologise for my sketch, not fabulous, but it'll do. And if you again, this is a cubic graph, and this is a quadratic graph. It's not x squared, but it is quadratic in nature. Okay, so quite important. This little table just sums up. So if you've got a maximum minimum on your original graph, that will be where you cut the x-axis on your gradient graph. You've got a point of inflection, that's where it touches the x-axis. Positive gradient on your gradient graph, you will be above the x-axis. Negative gradient below the x-axis. A vertical asymptote will also be a vertical asymptote at the same place, and any horizontal asymptote, when you do your gradient graph, will become a horizontal asymptote that is the x-axis. If you just have a little look at this, you can see there's a point where the gradient is 0, and that matches to that one. That's a point of inflection, matches to that one, and again it touches the x-axis. And then you can see this has a positive gradient, positive gradient, positive gradient, and this bit of the graph here from here is above the x-axis, and from here to here that's a negative gradient. Oops. Negative gradient, negative, and again this bit is under, and then again, okay, and then more negative, more negative, more negative, and it's still underneath. Okay, and it's sometimes useful to draw gradient graphs one underneath the other if you can. Okay, so let's have a look at these two. I'm just going to draw these. I'm going to draw them in pink so they stand out. So the first one, I've got a stationary point at when x is -1. So I'm going to map that down here. I'm going to put that there. Okay, I've got another stationary point there when x is 1. I'm going to put that there. You can see that this is negative, negative, so this will be underneath. Okay, like that. And this is positive, positive, and also positive, positive. So this will come up like this. And you should end up with something that looks a bit like a quadratic curve. Okay. This one, the second one, you've got, this is your only stationary point. Okay, so that will go here onto the x-axis. Now, this is negative gradient, negative gradient, negative gradient. So in other words, this is coming up like this. Okay, and then what you've got then is here, this starts to go positive, positive, but it then starts to shelve off. So here is the place where you've got your maximum positive. So it goes up to a maximum, then starts to come back down again, but it's still above the x-axis, and then it trails off, and you will have a horizontal asymptote of the x-axis because you had a horizontal asymptote there. Okay, that goes onto the x-axis. Right, now the last bit of this is optimization, modelling with differential equations, and I'm going to do 2 questions modelling. Now they all usually come in the same form, so let's have a little look at this question. It says a large number of open boxes are to be made, and each box must have a square base of length x centimetres, height h, and a capacity of 4,000 cubic centimetres. Find the dimensions of the box which contains the minimum area of cardboard needed. Right, so each box has a square base of length x, has a height of h, capacity or volume of 4,000, and I want the dimensions of the box which contains the minimum area of cardboard. Right, so the first thing I'm going to do is I'm going to draw a little diagram. So over here, I draw the box. there's my box. It's got, that's X, and that's H. And remember, it is open. It is open, it has no lid. So the first thing I'm going to do is write down the piece of information I've got. I know that the volume is 4,000. Okay. I want minimum A. Therefore, dA dx must equal 0. I want to minimise the area. I want the gradient to be 0. Okay. Now you know that the volume of a box is x squared h. Therefore, x squared h must equal 4,000. H equals 4,000 over x squared. And that piece of information is going to be quite crucial. But, well, I'm also dealing with area. So I'm going to think about the area of this box. And the area is made up from the bottom, which is x squared, and 4 sides. And the 4 sides are identical. So I've got 4xh. The front, the back, and the 2 sides are all xh. What I'm then going to do is I'm going to substitute h into that. So I get A equals x squared plus 4x, and then it's 4,000 over x squared. That then gives me A equals x squared plus, and that will be 16,000 x to the minus 1. Okay. I'm then going to differentiate that. dA dx equals, that's 2x minus 16,000 x to the minus 2. Remember what that is in disguise, that's the same as 2x minus 16,000 over x squared. Okay. We know that we want to set that equal to 0. So therefore 2x minus 16,000 over x squared equals 0. Cross multiply by x squared, therefore you get 2x cubed minus 16,000 equals 0. Therefore x must equal 20. And therefore, okay, your dimensions are 20 by 20 by 10. Because if you put x equals 20, I'll just highlight that. If you put x equals 20 into your formula for h, you get 10. And that's the dimensions of the box. Now, often with a question like this, they break it down for you. Now, you will notice I've not done question 1, and I'm not going to do question 4. Those are left for you to do. So let's look at what happens usually with an exam question. Okay. So this is a standard exam question, and they will often break it down for you. So let's have a little look. So you have, it says, a solid cylinder has a volume of 16 pi cubic centimetres. You need to express height in terms of its radius. So the first thing I'm going to do is I'm going to draw a diagram. There is my cylinder, very bad diagram, but it doesn't matter, with a radius of r and a height of h. So you're going to use basic piece of information. So you're told that V equals 16 pi. And you know that the volume of a cylinder is pi r squared h. Therefore, 16 pi must equal pi r squared h. And therefore, h must equal 16 over r squared, because of course the pi's will cancel each other out. Okay, and that's part 1 done. Okay, it then says, and we're going to use part 1, so that's quite important. It then says, show that a formula for the surface area of the cylinder can be written like this. So the surface area of the cylinder, you've got your big triangle, which is 2 pi rh, so that's the circumference times h, plus 2 pi r squared, and that's the area of the top and the bottom. You're then going to do is you are going to substitute, and I'll highlight it in red, your 16 over r squared from part A. So you get A equals 2 pi r, and it's 16 over r squared plus 2 pi r squared. And again, notice what happens. This one cancels with one of those, and then you bring 2 pi out as a common factor, so you get 2 pi, and you're left with 16 over r plus r squared. Now, that's us done, but please just remember that A is going to be 32 pi over r plus 2 pi r squared, and you see why we need that. Now the next part C says find the minimum possible surface area. Okay, so minimum surface area. Now that means minimum surface area is dA dr equals 0. Minimum surface area. So we're going to take A equals 32 pi r to the minus 1, that's from up there, plus 2 pi r squared, and we're going to differentiate it. dA dr equals negative 32 pi r to the negative 2 plus 4 pi r. Okay, we've already said we'll get our minimum when dA dr equals 0. So therefore, negative 32 pi over r squared plus 4 pi r equals 0. We're going to divide by pi, and we're going to times by r squared. So therefore, we're going to get negative 32 plus 4 r cubed equals 0. If you solve that, you get that r equals 2. We're going to sub to the formula for A. We can use any one we like. We can use the one at the top. Okay, so you're going to get A equals 2 pi, and that's 16 over 2. I'm just using the form up above, plus 2 squared. So A equals, and it comes out as 24 pi centimetre squares, and that of course is an exact answer. So often what happens, like I say, when you're doing optimization questions, they will break it down for you, okay, but you are using differentiation, and even if you cannot get to part B, you can still do part C by differentiating and just try your best to work perhaps exactly or inexactly. Right, now what you now need to do is you need to do exercise 12J and exercise 12K, and that is this chapter finished.